And if I recall, right, I think I basically said, okay, here are the naturals, here are the integers, which one's bigger? And you know, for the most part, people are like, they're equal. And yeah, they're equal. And the naturals and the rationals, are they equal? Yes, they are. And then the naturals and the reals. And we said, oh, look, the reals are actually, you know, strictly bigger. So we're actually going to go through the proofs of that. Now, there's a couple of proofs that you can do for the equivalence of the naturals and the integers. So in that case, it's actually quite possible to set up the bijection itself. But the bijection is a little bit hard to write down, but basically the bijection, maybe let me state this as a proposition. I kind of want to prove this in a different way, but I think it's useful to see just as kind of like, here's how you do these bijection arguments. So proposition, the cardinality of n is the same as the cardinality of z, or equivalently, we could just say the integers are countable, right? That's another way of saying this proposition. Integers are countable. Okay, and the dirty proof to this, which is somehow feels unsatisfying, because if you write it down, everyone will be like, yes, I believe that. That makes sense. But it's a little bit tricky to actually write down the function which does it. So what I'm going to do is you're basically going to define a function which does this. I'm going to define f from n to z as follows. And if you want, you can actually try and code this. So here I'm going to draw, let me use a different color. Here I'm going to draw the integers, right? I'm going to say this is 0 here, 2, 3, 4. Yeah, let's go a couple in each direction. 3, 4, like this. 1, 2, 3, 4, right? So here's my copy of z, and I've just written it on a number line, like so, okay? And again, I need to bijectively map this onto the naturals, or vice versa, right? The naturals onto here. So basically, this is what I'm going to do. So I'm going to say, let's pretend for now that 0 is a natural number. So 0 is going to map to 0. And then I am going to come over here, and 1 is going to map to 1. And then I'm going to come over here. And this is going to be what 2 maps to. And then I'm going to come over here. This is going to be what 3 maps to. And I'm just going to keep alternating like this. 4, 5, and so on, right? 6, 7. So the map is just going to alternate, right? 0 maps to 0, then to 1, to -1, to 2, to -2, to 3, to -3, and so on and so forth. So if you want, it is actually possible to write this thing down, do it as like a piecewise function sort of thing, because, you know, immediately you'll notice that all the odd numbers map to the positive integers and all the even numbers map to the negative integers, whatever. You can write this down, but I think it's quite illustrative if you actually draw it. And very quickly, you can be convinced that this is a bijective map, right? So let's think about it. It's certainly 1-to-1, right? Like I never hit an integer twice, right? Because every time when I swoop over to the other side, I go to the next free integer. So it's definitely 1-to-1, and it's definitely surjective, right? I definitely in this process will eventually hit any integer. You can be like, oh, well, you know, will you ever hit 1,000? And I'll say like, yeah, eventually I'll hit 1,000. Will you ever hit -1 billion? Yeah, eventually I'll hit a -1 billion. No matter what integer you give me, eventually this process will hit it, right? So it is surjective. So this, but you can see like this is not a very in some sense, it's not satisfying because you didn't like prove injectivity and surjectivity. I kind of like waved my hands around it and it was like just hands, right? The proof works. So, but this is a totally valid proof in some sense, right? Because again, I can show it to you and hopefully you're like, yes, this obviously does work. So I'm going to actually prove it in a slightly different way, a way that I think is slightly more satisfying. But if you don't, right, in order to do it, I have to prove a fairly major theorem first, that the countable union of countable sets is countable. And that's kind of overkill for this. Can we do n/2 for all evens and -n+1/2 for all odds as like what? As an inverse map? Divyansh, is that like what you're trying to do to show that it's bijective? Well, no, you don't want to do it from naturals to integers, because think about what your first thing is. So if n is a natural, you're saying, oh, I see what you're saying. Yes, n over 2 for all evens. So that's not what I've drawn. I guess that's if you actually started by going to the left instead of the right, because you're going to map 2 to 1 and 4 to 2. And that's totally okay. But that's kind of like, that's not what I've drawn. But that's, just by yours is if you'd started and from 0 and went to -1 first and then 1. But yeah, I think that should probably work. But then you still have to prove that that function is surjective and injective, right? You have to prove it's bijective. And what I'm saying here is that's not hard. That's not a hard proof. But I think if I just written down the piecewise function, you all would have taken a second and be like, I don't like, what is that thing doing? Whereas if I draw this picture, you're like, oh yes, clearly this works. Do you know what I mean? But I encourage you, use Devianch or my function and prove that it's bijective that way, right? I think that's a good exercise. So you can try that. But like I said, we're going to come back and I'm actually going to prove it in a more satisfying way once I have a slightly stronger result, okay? So I'll come back to this. I'm going to say, to be continued down here, to be continued. All right, and we'll come back to this proof and we'll prove it in a slightly different way. So before that, what I want to do is I want to prove this theorem. So a countable union of disjoint countable sets is countable. So a countable union of, and they don't have to be disjoint, but it actually just makes the proof easier if they're disjoint, but disjoint is actually harder, right? So a countable union of disjoint countable sets is countable. Okay, and if we wanted to translate that into the language of mathematics, so not just English, but the language of mathematics, we'd say for any collection of sets A sub I for I in I, where I is countable, we have that the cardinality of their union is also countable, right? So you can see the math way of writing this down is maybe a little bit more complicated, whereas the English way is pretty nice. The countable union of disjoint countable sets is countable. I didn't write the disjoint part in, don't worry about it. But this is the theorem that we want to prove. And the proof of this is super slick. Like it's easily one of my favorite proofs of all time. It does require that you know a little bit of something about the prime factorization theorem, like basically the fundamental theorem of arithmetic. And I'm hoping that you've all kind of seen that before. Have people seen the fundamental theorem of arithmetic? Nobody's seen the fundamental theorem of arithmetic? Okay. Okay, so there's yeses and nos. The class is a little bit split on this. Basically, the fundamental theorem, yeah. So the fundamental theorem of arithmetic is that every natural number has a unique decomposition into primes, right? i.e. every number can be factored into its primes, right? And that factorization is unique, right? So that up to reordering the primes, there's one and only one way of doing that. Yeah, sure, right? So I think like many of you probably knew that this was true, but this goes by this fancy name, the fundamental theorem of arithmetic. So the proof of this fact, super slick, right? Super slick. This is one of my favorite proofs, just kind of like of all time. Because think about what it is. Each of these sets could be infinite themselves, right? But infinitely countable, right? Like each of these things might be a copy of the integers, each of these sets A sub I. And then we might have an integer's worth of them, right? So we could have infinitely many sets, each of which have infinitely many elements. And we're going to union them all together. And we claim that, yeah, we can actually, that thing is still countable. And not only that, the way that I'm actually going to prove this is with Cantor, Burnton, Schroeder. And I'm going to be like, clearly the natural numbers, or basically I'm going to try to embed this into the natural numbers, right? I'm actually going to do and show that there is an injective map from this potentially infinite union of this infinite union of sets with infinitely many elements into the naturals. Okay, so watch this. This is crazy. All right, here's what we're going to do. So I is our indexing set, right? It's the thing which keeps track of which set I'm working on, which of the a sub i's I'm working on, and we're told that that's countable. So we know that there exists a function f from I into the integers, which is injective. Okay, and you'll notice that I put a little hook on my arrow here. And that's usually just mathematically. If you want to indicate that your function is injective, you just put that little hook on it. That means injective. You should still say it in terms of words, but notationally, that's how you indicate that you're working with an injective function. So we know that there's an injective map from our indexing set into the naturals because, we were told that it's countable. Okay. We also know for every I, there exists a function g sub I from a sub I into the naturals, which is injective. Okay, so the function f here keeps track of the fact that we have a countable collection of sets. And then the g sub i's is, I said that each of the a sub i's was countable. So g sub I is the injection which proves that a sub I is countable, right? And so it has to be indexed by I as well, because that injection is going to change for each of my sets, right? A sub 1, a sub 2, a sub 3, they each need different injections. So we have one for each of them. Now here's what I'm going to do. So we're going to define a map, let's call it maybe capital F, from the union into the naturals. And what I'm going to do is I'm going to take an element A and I'm going to map it to 2 to the F of n, 3 to the G sub n of A, where A is in A sub n. Okay, and so we have to think about this for a second. Okay, so I'll give you all a second. If you're taking notes, I'm going to give you a second to write it down because we have to think about what the hell is this function doing? What is n, right? Because somehow this n shows up in the evaluation of this function, but like there's no n's on the left-hand side. But there is an n on the left-hand side. We just have to, be careful about it. We've got to think about it. But basically what this function does, right? So it says, you give me an element in this countable union of countable sets. Give me an element. It's in one of the AIs, right? So it's in A sub n. And again, we've kind of assumed that the A sub i's are disjoint. So it's actually in only one of the A sub n's. So it's in A sub n, and that's where n comes from. Then what I'm going to do is I'm going to map it to 2 to the power of f of n and 3 to the power of g sub n of a, right? And I claim that this is an injective map. And why? Can anyone just tell me in basically one sentence why this map is injective? Yeah, because each number has a unique factorization into primes. 2 and 3 are prime numbers, right? Exactly. So because every element comes from a unique, right? Every A comes from one and only one of the A n's. And then I have the G n's are being an injection. This means that every element on the left-hand side in the map will have a unique power of 2 and a unique power of 3. So what this thing here is doing, this is keeping track of what set you came from, right? So every element in the same set will have the same power of 2. Right? So every element of the same set has the same power of 2. But then they'll all have different powers of 3, right? Because G sub n is an injection, it maps, in a single set, it's going to map each of those elements to a different power of 3 because that's how it works, right? So if I give you, a bunch of numbers that, whose images are like 2 to the power of 4, 3 squared, and 2 to the power of 4, 3 to the 10, you actually know that those two elements originated in the same set and are actually, different elements because they have different powers of 3. And then, yeah, like I was saying, the power of 3 here tracks the element themselves within the set. Tracks the elements within the set. Okay. Yeah, it's kind of like an ID tag, right? So the power of 2 tags what set you're from, and then the power of 3 is your individual ID, right? And I mean, like, I don't want to do this analogy because, usually when you start IDing people, it's bad. But okay, so let me use the following thing. So in Canada, for example, right, everyone has a social insurance number, and probably whatever your home country is has something similar. Now in Canada, social insurance number is 9 numbers long, and the first number indicates what province you were born in, right, or what province you got your social insurance number in, and then the rest of the numbers uniquely identify you within that province, right? And so this is doing the exact same thing. The power of 2 tells you like what province you came from, right, if each of the sets is a different province, and then the 3 is the unique part of that which corresponds to you, right, which identifies you as an element of this set. And again, we know that this is an injective map because the fundamental theorem of arithmetic, right? Every number has a unique prime factorization. So we can't have 2 of these things mapping to the same thing because this is the prime factorization, right? So by the fundamental theorem of arithmetic, I don't want to write that whole thing out. I'm just going to call it the FTA. Okay. And again, if you want to write that one up a little bit more carefully, by all means do it. Be like, suppose that f of a is equal to f of b, right? Then that means that f of a so f of a is equal to f of b. So that means that 2 to the n, 3 to the m is 2 to the k, 3 to the k, or 3 to the l for some m, n, k, and l. But by the fundamental theorem of arithmetic, the powers of 2 have to be the same and the powers of 3 have to be the same. So a is equal to b, right? That's how you would basically actually do this if you wanted to write it out. So we can map all of the natural numbers with more. It depends on what you mean. Like, so can you expand on that, Ruyi? Like, so we can map all of the natural numbers with more prime numbers. Like so first of all, right, 2 and 3 are not special here, right? I could have used any primes. And notably as well, this misses a lot of naturals, right? Like this really actually spreads the numbers out. So maybe I'm misunderstanding what you're saying, but if you want to elaborate on that, I'll be happy to answer it. But while you're doing that, let me set up the next one. Okay, so this is now me revisiting this because I kind of just i.e. 5 to the power of h of k. Well, we don't have an h though, right? So the only reason I used 2 primes is because the first one is, again, it's going to keep track of what set I came from. And then the second prime keeps track of what element I am in that set. If we had something else we needed to keep track of, we could definitely just use more primes. And so that kind of gives you this cool way of, expanding this out if you really wanted to. Totally, absolutely, you could do that. It's just in this case, we don't have an H, right? But if you did, yeah, totally, you could do that. And it would still work, right? It would be the exact same proof. By the fundamental theorem of arithmetic, prime factorizations are unique. So yeah, if you wanted to do that, that would be totally okay. Okay, so I'm going to prove this one in a way that I like a little bit more. But this proof will use Cantor, Bernstein, Schroeder. And here's how I'm going to do it. Yeah, no problem. Okay, so we know already n is less than or equal to z, right? I don't think I need to prove that. Can we prove using the nth prime is to the power of a? Well, you don't know what a is. Right? A could be like a word. So you definitely don't want to exponentiate, right? You don't want to take it to the power of a. You need to capture what natural number belongs to a by using this g sub n function. So you kind of can't avoid using f and g in that sense. And same sort of thing, like you don't know what the indexing set is, right? You could index by, for all we know, capital I is like apple, pear, orange, happy face, sad face. Right? They're not natural numbers. They're just some sort of set that happens to be countable. So we have to use f and g. And then in terms of your just like maybe mapping to the nth prime to the power of a, that's interesting. The primes are certainly countable. but I don't think you're going to get enough. Oh, you know what? That actually might work. That's an interesting proof. Yeah, like maybe try writing this one out. So you might say something like the primes are countable. So we have, some sort of injective map from the primes into the naturals. And then I'm going to define the map A maps to the nth prime, but using the map, right? Using that injective map, and then to the power of G sub NA, that might work. Give that a shot. See, like try writing it out. I think that actually will work. That's a nice one. I like it. Right? Yeah, the only reason we probably don't use it is we then need another function, right? Because we still have the function f, and now we need to combine that as well with the function that maps the primes into the naturals. So we'll end up kind of composing those two maps, which is why I don't do it that way. But I think that would work. I think it's a good idea. Yeah, so try writing it up and see if you can get it to work. Okay, so the naturals are certainly a subset of Z because, I mean, there's an obvious injection, which is just to include the naturals into the integers, right? Like the naturals are a subset of the integers. So certainly their cardinality is less than or equal to, right? Because you literally just say, take the identity map from the naturals to the integers, and you've got your injective map. So we want to prove the other direction. Now, this is how I'm going to do it. So I'm going to define f from Z to N. And again, I want to define an injection here. And I'm going to take, what am I going to do? I'm going to define N, and I'm going to map it to the sine of N and the absolute value of N. Right? So for example, here I'm going to take f of 3, and that's going to be equal to 1, 3. But f of -5 is equal to -1, 5, right? And so all this is doing, right, is it keeps track of basically the sign and the absolute value of the integer itself. And, oh, sorry, this isn't n, this is 0, -1, 0, 1 cross n, right? And this is, again, certainly injective. I'll leave the proof to you. So certainly f is injective, right? Because the only way that two things have the same number on the right is if they have the same absolute value. There's only two numbers that have the same absolute value, right? So in this case, 5 and -5 have the same absolute value, but then the first element of the tuple is going to be different, right? Because if it's +5, you're going to get 1, 5, and if it's -5, you get -1, 5. Those are different. So certainly f is injective. So we get that that is true. And this is the same thing as the union of 3 copies of N. Okay, so this is the union. So this is the same cardinality. No, actually, this is just equivalent to, maybe let me write it like this. This is equal to -1 cross N union 0 cross N union 1 cross N. Right? So it's a countable union of countable sets and therefore is countable. And so by Cantor, Bernstein, Schroeder, I've now shown that there is an injection from Z to N. And we already knew from the beginning that there was a injection from N to Z. So both of these by Cantor and Bernstein, Schroeder tells us that, in fact, they're equal. So by Cantor, Bernstein, Schroeder, I'm just going to call it Cantor, Bernstein. Like so. Okay. So knowing that the countable union of countable sets is countable, super powerful, because now immediately you can, right, like that really expands your repertoire in terms of being able to inject things into other things, right? It becomes very, very powerful. Are there any questions about that? Guys, I'm not 100% certain if you're all okay with what I just did there, right? Like, so if there are any objections, you should definitely like yell out and say, no, something's fishy there. So hopefully I hope you're all okay. How's the naturals a countable set? By definition, the naturals are countable, right? Because remember, so the definition of being countable is that there is an injection from S into N. And the identity map is, an injection. So the natural numbers mapping to themselves by the identity is an injective map. So that would tell you the naturals are injective. Can I explain why it's -1, 0, 1 cross n, since there's 2 terms in the tuple, but 3 elements in the set? Okay, yeah, so I'm just saying here that the first, this thing here, the -1, 0, 1, this is the thing where the sign lives, right? This is the sign of n. And then when it's cross n, this is the absolute value of n part, right? So when I said f of n is equal to sine n comma absolute value of n, this is where I'm saying this lives. Is 0 cross n just 0, 0? No. So everyone remember from the formative handout, right? A cross B are the tuples such that A is in A and B is in B, right? So in that case, 0 cross n looks like 0 n for n in the naturals, right? So it looks like every natural number, but it just has a friend 0 on the left-hand side. Okay, so Yvonne, does my thing make sense here? About why it's -1, 0, 1? And remember, the only reason, okay, perfect. And the only reason 0 is in there is because we usually say that the sign of 0 is 0. If you wanted to say that the sign of 0 was 1 or something, you could do that, and then you could actually get rid of the 0, right? And then it would just be -1, 1 cross n. But it doesn't really make that much of a difference because it's still a countable union of countable sets. Yuanji, does it make sense what 0 cross n is? Do you see that it's not just 0, 0, like it actually has a bunch of elements in there?
Yeah, I got it.
Okay.
Yeah, the 0 is a little bit confusing because I'm not sure like what's the sign of 0 actually means. So
right, exactly. Yeah. And yeah, so there's some ambiguity there. We're just going to say, I think the sign of 0 is 0, right? And that'll just make our lives a little bit easier. What do you mean by countable union? Okay, so a countable union means that I have a countable collection of sets, and I'm going to union that collection, right? So a finite union would be if I were unioning a finite number of sets, right? So a finite union would be something like, why is it not erasing? So A1 union A2 union A3, right? That's a finite union because there's only 3 sets in there. Whereas a countable union, is an infinite union. So I could be like, whoop, and then just do that forever, right? For every natural number, there's a set A sub n, and I'm going to countable union them all. Are we going to include 0 in the naturals? Right. Yeah, I am. So I think I'm a little bit against my colleagues on this. In that one, I usually do consider 0 a natural number, but it's usually for context for me. So there are times when I want 0 to be a natural number. There's times when I don't want 0 to be a natural number. And so I flip-flop depending on what I want. I am generally okay with you doing the exact same thing. And if there's ever ambiguity, I will tell you whether 0 is considered a natural number or not. And if it comes up in a test or something, you should just ask. Right? Like if you think it makes a difference and I didn't tell you that 0 is a natural or not, just send me an email or throw it on Piazza or whatever and be like, hey, are we considering 0 to be natural for this? And I will tell you, right? I'm not sure why Cantor, Bernstein, Schroeder is true. That's fine. I didn't actually give I didn't give you all a proof of it. I would say for this to check out the 102 notes. I am working on creating a handout for that, but yesterday was just a dumpster fire for me. We had I don't know if you know, I'm the person who hires all the TAs for the department, and we had a TA drop out, right? Like tutorials have already started, right? So we had a TA drop out for a very hard to fill class. And so I spent like half the day trying to find another TA for that. Do I have any worksheets for similar problems? Actually, in this case, again, I would probably suggest grabbing the Math 102 notes. I think Shai has a lot of problems on cardinality because they actually do this as part of 102, right? So if you want to check that out, that's probably a great place to find some problems. We're like, this isn't going to be a huge focus of this class. The reason why I'm doing this is I do need you to know that these sets are countable, because I'm going to say things like the word countable and uncountable later in the class, and you need to know what these words mean. So that's why I'm covering them now. But this isn't going to be a huge focus for us. So I would say it's probably not worthwhile to go into it in too much depth, unless you just think it's cool and you want to practice it more, which is awesome. But I would say not to worry about it too much, right? I'm really just going through it because I need you to know what these words mean. So hopefully that clears up much of it. All right, so let me just very quickly do this one. So proposition, the rationals are also countable. Okay, and we're going to do the same thing. I'm going to say, listen, clearly n is a subset of the rationals, again, just by using the inclusion map. So certainly n is in Q. And then for the other direction, we're again just going to construct an injection from the rationals into the naturals and then use Cantor-Bernstein in order to prove the result. Okay, so we're going to define a function f from Q to, what do I want to do here? Let's do Z cross n. And here I'm going to again show you how the natural numbers will have 0 or not, depending on how I feel. Okay. So the map I'm going to define from the rationals, I'm going to define it into Z cross n. Okay, and what I'm going to do is I'm just going to say pluck out the numerator and the denominator, right? And put the numerator on top and the denominator on bottom. And I'm saying that if we have a negative fraction, the negative sign is always going to go into the first tuple, okay? So as an example of this, maybe we'll have something like, I don't know, 3/8 will map to 3,8, right? But -15/7. The negative will always go into the first thing, right? Because that's the integer portion. So the integer or the negative portion will always go into the first argument. Now the GCD AB thing, I don't really want you to worry about that. This just guarantees the map is well defined, right? This says that A over B is already in lowest terms, right? So 1/2 is going to map to 1,2, and we can't apply this map to 4/8 because it's not in lowest terms. So when you want to figure out what 4/8 is, you first have to reduce it to 1/2 and then map it. What do you mean by there are no repetitives? Like there's no, because yeah, the question is whether or not this map is injective, right? So is that what you're asking? Like, right, and we're saying no. We're saying that in order to figure out what 4/8 is, you first have to reduce it to lowest terms, 1/2, and then map it, right? So 4,8 will never occur. 4,8 is not in the image of this map. 1,2 is, but 4,8 will never be hit because 4/8 is not a rational number. Yes, yeah. So GCD AB equals 1 just says that, right, GCD stands for greatest common divisor. So this says that A and B don't share any common divisors, right? And that's what it means to be in lowest terms. So this just says the fraction is in lowest terms. So you've reduced it as much as possible. And then this guarantees, yeah, and exactly, GCD of 4 and 8 is 4. And so that's why 4/8 doesn't work. You're not allowed to do it because it's not in lowest terms, right? There's still divisors there. So this guarantees that the map is injective. And again, you can check, but basically it says that in lowest terms, all fractions are unique, right? There aren't two fractions that when in lowest terms are different numbers, but their fractions are the same. Does that make sense? Right? Like there are no two numbers which are different, but their lowest term representation is the same, right? Certainly all fractions are unique in that sense. And so this map is, again, clearly injective. You can write up a full proof of that if you want. And Z cross N is again a countable, no problem. Z cross N is again a countable union of N's. Is a countable union of countable sets. And so is countable. So I hope you appreciate like how powerful that theorem that I did earlier was, like that the countable union of countable sets is countable. It opens up a lot of things, right? So this tells us that Q less than or equal to Z cross N less than or equal to N. And now by Cantor-Bernstein, we've got equality, right? Which is what we wanted. Okay, so remember, like the takeaway here is not, again, I'm not super worried. You know, I've been a little bit quick. I'm not going to lie, because I probably could have been more rigorous about showing that these functions are injective. But again, I want to emphasize that that's not really our goal here. My goal is not to worry about too much about injectivity and surjectivity of these sets and countability and cardinalities. That's not going to be the focus of our course. But you need to know naturals are countable, integers are countable, rationals are countable, and finite sets are countable, right? So when I say countable, you know I could be referring to any of these things and anything in between. And then what we're about to do now is Cantor's diagonalization argument, which says that the real numbers are strictly bigger, right? That the real numbers are not countable. And so when I say uncountable, I mean something which is strictly bigger in cardinality than the natural numbers. All right, so that's all I want you to get from this. So I'm going to call this a theorem because I think that this is a pretty critical theorem. The reals are strictly bigger than the naturals. Okay, this is an awesome theorem. I love it. It's a lot of fun. However, in my experience, students do often struggle with it the first time they go through it because it is a contradiction proof, right? And contradiction proofs, especially if you're first kind of getting used to them, they are a little bit tricky because you're like, wait a second, what? We proved nonsense. And you're like, yeah, it was the point. I wanted to prove nonsense. So what we're going to do is, for the sake of a contradiction, let's assume that the real numbers are in fact countable. Okay, so for the sake of contradiction, not everyone starts out their proofs with that sentence. I really like to, because you signal to the reader very, very quickly that you're doing a contradiction proof. So I would recommend that, but you don't have to. So for the sake of contradiction, assume that the reals are in fact countable. Okay. Now, what countability means, again, we know that this means that there is in fact a bijection between the reals and the natural numbers. Alternatively, what it means is you can actually just list them all out. So let's write down all of the real numbers. So let's enumerate them. The reals. Okay, so I'm going to say R1. Wait, do I normally, let me just double check this. I'm pretty sure when I do it, I normally even just do the numbers between 0 and 1. Yeah, let's actually just do, let's just do 0, 1. Sorry if you were writing that down. So for the sake of contradiction, we're just gonna, let's just do the open interval 0, 1. Okay, and because we know that has the same cardinality as R, right? We proved that last class. We know that has the same cardinality as R, but it's going to be a little bit easier because I know then that it's just 0 point something, 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 right? So enumerate these as R1 is 0 point D1, 1, D1, 2, D1, 3, D1, 4, D1, 5, R2. I'm going to have to, this part is a little bit kind of boring because I'm going to have to write out a couple of them because I want to show you what we're doing. It's called Cantor's diagonalization. So I'm probably going to have to draw a diagonal at some point. D31, D32. So these aren't powers, right? These are just indices. D41, D42, D43, D44, D45. Okay. And so on and so forth. So there is a bijection from the naturals to the reals. And I'm saying, look, the first of those real numbers, what does map 1 map to? It maps to R sub 1. What does 2 map to? It maps to R sub 2. What does 3 map to? It maps to R sub 3. So being countable means that you can actually just list all of them and actually write them down. Okay, that's one of the properties that being countable gives you. Now, when I write this, again, I want to make it clear that D sub I j, so this isn't raising anything to the power of j. This is saying that this is the jth decimal of R sub I. Right? So there isn't any powers. It's just a double index because we've got a whole bunch of indices going on. Okay. And now what I'm going to do is I'm going to define, did I not write Cantor? Oh, okay. I didn't write it down. So I'm going to have to make it up as I go. So now I'm going to claim, so we've written down every single real number here. And what I'm going to do is I'm going to construct a real number that is not in this list. Right. And that's a contradiction because I said, listen, every single real number is right here. I'm going to write them all down. Right. And then if I can construct a real number which isn't in this list, well, that's a bad thing because I'd written them all down. So how can I then write down a number that isn't in this list? Right. That's not possible. So here's what I'm going to do. So define a new real number R. Yeah, let's just call it R as follows. So R is going to be 0 point D1, D2. And now this guy doesn't have the superscripts. D4, D5, dot, 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 where DI is equal to, let's say, what do I want here? 0 if D, okay, now I need to get my indices straight. So D I is equal to 1 and 1 if D sub I is not equal to 1. Okay, here's the diagonalization portion. All right, so what it's saying is, I want you to look at these numbers. This is the diagonal part. Okay, so look at each thing that I've circled in yellow. If that number is 1, then the new thing that I define is going to be a 0. If it's not a 1, then you're going to let it be 1. You're going to let D sub I be 1. Okay, does that kind of hurt your brains? Do you see what's going on? Are there questions about this? I suspect there should be. Yeah, okay. Maybe let me write down an example. Let's say we actually have numbers. Okay, this is normally how you would You would not do it this way, but I think it might help if I actually have some numbers here. 2, 4, 6, whatever. Okay, so let's say when I'd written these down, this guarantees that R is not in R sub I. Yeah, exactly. Well, it guarantees it's not equal to R sub I, right? So the d-ith decimal for R is different from the ri's in the d-th decimal. Right, exactly. So it's different from every number. But so I see that you two have got it, but let me kind of go through this for the people who don't see it. So I'm going to look at this diagonal here, right? And I'm going to create a new number as follows. So the number R, okay, so I'm going to look at this first decimal place. It is a 7. So according to the definition right here, since this is not equal to 1, I'm going to let this decimal be a 1, right? So that gave me this decimal. For my next decimal, oh, this is actually a 1, right? So I'm going to put a 0 here. This is not a 1, so I'm going to put a 1. This is not a 1, so I put a 1. Does that make sense? Yeah, exactly. And you would just keep doing this, right? You do this for every single natural number that exists. And the point is that this new number that I have created is not any of the numbers that are in my original list. Because I've guaranteed at every single step that the ith decimal place of the numbers in the list on the left is not equal to the ith decimal place of the number on the right. Is decimal notation for real numbers required for this proof? What if we use binary representation? You could use binary representation, Tianran, and then just kind of flip them. You do have to be careful, though, if you use binary, and I'll explain it at the end why you have to be careful, but yeah. Sure, so you change the digit then, Sultan. So you change the digit in the sense that if the number is a 7, right, like just to make the construction easy, if the number is a 1, you're going to change it to a 0, and then otherwise the number is going to be a 1, right? And this is the usual thing with math, right? There's usually some sort of relatively simple idea underlying it, but when you actually write it out mathematically, you kind of lose some of that idea. So is everyone okay with how this construction works? Are there still questions about that? Because I'm running out of time here, so I might go a little bit over if that's okay. Right, so every number is either a 0 or a 1, but the important point is note that R is not equal to R sub I for all I, right? Because by definition, you've made sure that R and R sub I have different decimals, right? The ith decimal place of R and R sub I are different. So these two numbers can't be equal. And therefore, you've now constructed a real number, which is not in the list. In the list, and that's a contradiction. Right, so R is strictly bigger. Not that there are infinitely many real numbers, Wei-Ming. This is the proof that there are more real numbers than there are natural numbers. Yeah, I think that's a really cool proof, right? And so if you're struggling with it a little bit, like take a second to think about it. Again, this is a really important thing. And the fact that this can actually be extended to prove that the cardinality of a set is never equal to the cardinality of its power set. The power set is always strictly bigger. So that generalizes to that. But yeah, this is what's going on. But yeah, otherwise, everyone, I'm sorry I went like a minute or two over. This is going to cover it. Now, somebody asked, yeah, Tianran, you asked if we could do this with just 0s and 1s. Yes, but then you have to really be careful. And I think binary is probably the worst place to do this. But if you did it in ternary, like base 3, it would be much easier. And the reason for this is what you have to worry about. And you can use any numbers other than 0 and 1 here, right? Except for one thing, you never want to use 9. And the reason is that if you get 0.999999 at any point, if you just get this repeating series of 9s, that like becomes a 1, right? Do you all know this? right? 0.9 bar is equal to 1. These are the same number, right? So we have this issue in that the representation of real numbers is not unique. And you want to avoid this. So in binary, you'll get the same thing, right? So in binary, if you ever get the collection, where you get 1, 1, 1, 1, and this goes forever, that becomes like that, right? So you have to be careful. I would say binary is the worst place to do it, because at least if you're in base 3, you can guarantee that this never happens just by using zeros and ones, right? So if you're in base 3, you just use zeros and ones, you avoid this problem. And then, because we were in base 10, I also used 0 and 1s, but I could have used 3s and 5s or whatever. Just don't use 9, right? Whatever base you're in, don't use the highest number of that base, and your proof will be okay. Okay, everyone. So hopefully that makes sense.